Hi students, in the previous video we discussed what is the force acting on a current carrying conductor when it is placed in uniform magnetic field, and we also found out if two conductors are placed parallel to each other, and then what is the force experienced by the conductor, in which direction is the force experienced by the conductor, whether the conductors attract each other or they repel each other when current is flowing in the same direction or in opposite direction in the conductors. Now here, instead of two conductors, we are going to place a rectangular rectangular frame in a uniform magnetic field, and we are going to find out what is the torque experienced by the rectangular coil in the uniform magnetic field. P, Q, R, S. This is a rectangular coil or rectangular frame which is placed in a uniform magnetic field. The field is from north to south like this. Okay. We are going to find out what is the torque experienced by such a rectangular frame in a uniform magnetic field, rectangular frame of coil in a uniform magnetic field. So first what we do is we are going to find out what is the force, what is the direction of force in each of the portions PQ, QR, RS and PS. And we know, if we know the direction of magnetic field, if we know in which direction the current is flowing, then using Fleming's left hand rule, it is easy to find out the directional force acting on the conductor. So instead of the rectangular frame or rectangular coil, we are going to divide into four sections. Okay. So first let us find out what is the force, in which direction is the force acting in the conductor PQ. So for that we have to use the Fleming's left hand rule. Stretch your middle finger, forefinger and thumb in three mutually perpendicular directions. Now your middle finger indicates the direction of current, forefinger indicates the direction of magnetic field, and the thumb indicates the direction of the resultant force, father, mother, child. Okay. So now in this diagram, current is in the upward direction. Now field is from north to south, so field current in upward direction, field is from north to south, so direction of force is into the plane of the coil. So the magnetic field, force due to the magnetic field and current is into the plane of the coil. Into the plane, I will put a cross mark here, F, force is into the plane. Okay. Next, let us take the side RS. RS current is in which direction? Current is in downward direction. Field is again from north to south in this direction. Then what is the direction of force? It is directing towards us, that is out of the plane, isn't it? So direction of resultant force is outward. The dot mark to indicate the forces point towards outward of the coil. Okay, now let us see what is the direction of force, the resultant force due to field and current in the side PS and QR. Now one thing which we have to remember here is, in this case the coil is not placed exactly parallel to the field, which means if this is a rectangular coil, if this is the field is from north to south, the coil is not placed exactly parallel to the field, it is kept at an angle. Okay, it is not kept like this, it is kept like this at an angle with the magnetic field. Okay, so in this case we will take the portion QR. Current is towards Q to R, field is from north to south, it is kept at an angle. Okay, so the direction of force is pointing upward. Whereas when you take this side PS, current is in this direction, field is in this direction, force is pointing downward. But since the rectangular coil is kept at an angle, what happens is that we say the force acting on the side QR and PS are equal but is collinear. On sides PS and QR are equal and opposite and is collinear. Now what do you mean by collinear force? It's very simple. It is acting along the axis of rotation. Now in this diagram, the dotted line represents the axis of rotation, and one more thing I forgot to explain, that is theta. Here the angle theta is the angle between the magnetic field and normal to the plane of the coil, which means if this is the magnetic field, if this is the coil, then theta is not the angle between the field and the plane of the coil. Theta is the angle between the normal. If I take normal, normal will be pointing outward, isn't it? So theta will be the angle between normal to the plane of the coil and the magnetic field. Okay. So now let us see what is collinear force. Now I told you collinear means the force is acting along the axis of rotation, which means this is the axis of rotation in the case in our rectangular coil. This dotted line represents the axis of rotation. Now imagine there is a tug of war competition and two teams are standing on both sides of the rope and the ribbon is tied at the center. Now you know, for both the teams to win, they will be applying an amount of force in their direction. Now what if both the parties or both the teams are applying equal amount of force to this rope and they are trying to pull in the opposite direction? Definitely the ribbon will stay steady, which means the rope will be still. There won't be any effect of force applied by both the teams on the rope, and the rope won't move. Same way, in this case, in the case of QR, in the side QR and PS, the force acting is equal and opposite and is acting along the axis of rotation, in which one direction of force is pointing upward and there is other side the force is pointing downward. So equal and opposite force acting along the same line of action, which means no effect. So there will be no effect on this particular experiment on from the side QR and PS. Only the force which is acting on the sides PQ and RS will produce the torque. Now side PQ, the force is acting into the plane, and side QR the force is acting out of the plane. So what happens? Equal and opposite force constitute a couple and it produces a torque which will make the coil rotate clockwise direction. So let us find out what is the equation for torque experienced by such a coil when placed in a uniform magnetic field. Now we have studied the equation for torque in 11th standard. We know the equation for torque is tau is equal to force into perpendicular distance from the axis of rotation. Now force, what is the force acting on a current carrying conductor when placed in a magnetic field? It is F is equal to I L B. Now in our experimental setup, I is the current flowing. Now A and B are the length of the sides. B represent the length of the side PQ and RS, and A represents the sides PS and QR. So A and B are length of sides, isn't it? So in our case the force is due to the side PQ and RS. So L will be what? L will be equal to B. So torque will be, force will be F is equal to I B B. Now the question, what is the perpendicular distance from the axis of rotation? To find out the perpendicular distance, we have taken the top cross section of the rectangular coil, that is QR, and this side is A, this side is this angle is theta, then definitely the perpendicular distance will be A sin theta. So perpendicular distance is A sin theta. So we can write torque tau is equal to I L B A sin theta. Now I B B A sin theta. Now what is B into A? B into A is length into breadth area. So we can write this as I A B sin theta. Now if the coil contains n number of turns, Then the above equation can be written as tau is equal to NIBA sin theta, and this NIBA is a constant known as magnetic moment M. So we can write, NIA can be written as magnetic moment M. So the equation becomes MB sin theta, where M is the magnetic moment of the coil. Now this magnetic moment is a term which represents the strength of the coil, and it is similar to the electric dipole moment for a dipole. Okay, so in vector form, the above equation can be written as tau is equal to M cross. This is the equation for torque experienced by a rectangular coil. Torque experienced by a rectangular coil when placed in a uniform magnetic field. And theta, don't forget, theta is the angle. M cross B is MB sin theta. Theta is the angle between normal to the plane of the coil and the magnetic field. So let us consider the special cases here. First one, when theta is equal to 90 degree, that is when normal to the plane of the coil is perpendicular to magnetic field, or you can say when plane of the coil is parallel to the field. When plane of the coil is parallel to the field, what happens? When we take the normal and the magnetic field will be perpendicular to each other, so theta will be equal to 90 degree. In that case, torque experience will be MB, and is the maximum torque. Experienced by the coil in the external field. And second case, when theta is equal to 0 degree, it is when plane of the coil is parallel to the is perpendicular to the field. We get torque is equal to M cross B sin theta, that is tau is equal to 0 y, since sin theta sin 0 equal to 0. Now this is a very important derivation, because this is the principle behind the working of a moving coil galvanometer. Okay, so we got the torque experienced by a rectangular coil when placed in external field as tau is equal to NIB sin theta, or we can write MB sin theta, where theta is the angle between, again and again I am saying, theta is the angle between normal to the plane of the coil and the magnetic field. Thank you.